Have we found all string theories? In this video, I will try to answer this question. It will require a basic understanding of quantum field theory and symmetry algebras, but I will spend some time talking about the background material before coming to answering this question. According to popular belief, there are 5 different superstring theories, namely Type 1, Type 2a, Type 2b, heterotic SO32, and heterotic E8 by E8. On top of that, we have bosonic string theory, but it doesn't have any fermionic excitations in it. We can throw in 11-dimensional supergravity in this mix, and then we can get M theory. But have we found all string theories? We will try to make a classification scheme, and then we will locate the known string theories in that classification scheme. After that, we will try to see if there are some other possible string theories that we can get from studying this scheme. So let's start to build such a classification scheme. When strings move in the spacetime, they sweep a surface called the world sheet. This sheet is two-dimensional. A way to study string theory is to study it as a field theory on this world sheet. This field theory has symmetries which are referred to as world sheet symmetries, and those symmetries have symmetry algebras. Mostly when we talk about symmetry algebras, we mean the set of commutators of the generators of symmetries involved. Now, if the symmetry involved is conformal symmetry, then it turns out that two-dimensional conformal symmetry has infinite generators. These generators can be thought of as Laurent modes of a field. This field turns out to be the stress energy tensor. It is denoted as T of C, where Z is the location of the field. Every field has a property called the conformal weight. It is just a number and is denoted by H. It dictates the way that field transforms under conformal transformations. It turns out that for T of C, H is equal to 2. The modes of T of C are called the Virasoro modes, and the commutator of Virasoro modes is called the Virasoro algebra. Since Virasoro modes are modes of T of C, the commutator of Virasoro modes contains information about something called the operator product expansion, also called the OPE of T of C. OPE of a field T at a point Z with another field X at a point W denotes the product of T of C and X of W as a sum of fields and their derivatives. This sum can have a singular part because Z and W can come very close, and in that case, the product T of C times X of W blows up. OPE of T of C means OPE of T of C with itself, which means T of C times T of W. Now, it turns out that the singular part of T of C times T of W contains the information in the Virasoro algebra. We refer to T of Z times T of W as the current algebra or the operator algebra corresponding to the Virasoro algebra. T of C is correspondingly referred to as a current here. Now, if we try to make a string theory, we have two sectors of the theory called the left and right sectors. So we have to specify the symmetries and hence currents of both of these sectors. If the stress tensor is the only current in both of these sectors, we get the bosonic string theory. As an aside, conformal symmetry is not something that we put in by hand in bosonic string theory. Instead, it comes out as an inevitable condition to be fulfilled. The classification scheme that we are pursuing here paints the picture as if we put in the conformal symmetry by hand. This is not the case. Now, we can generalize this idea. The generalization comes with some assumptions that I will talk about in the following. We can think of more symmetries that have some other currents and write down their current algebras. Can we make new string theories in this way? One obvious symmetry to include is supersymmetry. Supersymmetry has a current called supercurrent. For this current, H equals 3 over 2. If we add stress tensor and supercurrent in both sectors of a string theory, we get type 2 string theories. Both type 2a and type 2b are in this category. They are different in some other regards. Let's develop some convenient notation here. We can label these theories by two numbers, n and n prime. N and n prime tell the numbers of supercurrents that we have in the left and right sectors respectively. Therefore, bosonic string theory is 0, 0, and type 2 theories are 1, 1. What about other n and n primes? Now, the critical dimension of a string theory is the maximum spacetime dimension of that theory. It is well known to be 26 for bosonic strings and 10 for superstrings. It turns out that if n or n prime is larger than 2, then the critical dimension is negative. So these theories don't make physical sense. So n and n prime can be 0, 1, and 2. We will now list the cases apart from the cases that we have discussed above. These cases are 0, 1, 0, 2, 1, 2, and 2, 2. We have not included the cases 1, 0, 2, 0, and 2, 1 as they are equivalent to 0, 1, 0, 2, and 1, 2 respectively. 0, 1 is nothing but the heterotic string theory. The two well-known heterotic string theories, that is SO32 and E8 cross E8, are in this category. They are different in other regards. The theories corresponding to 0, 2 and 1, 2 are interesting but mostly of mathematical interest. 0, 2 is used in some other places, for example for Landau-Ginzburg models. The 2, 2 theory is quite interesting because the critical dimension of this theory is 4, which is the dimension of our macroscopic spacetime. However, these 4 dimensions should either be all space dimensions, all time dimensions, or 2 space and 2 time dimensions, which is not the case for our universe. Damn it was so close. Until now, there were 2 unspecified assumptions that we were making in our analysis. First of all, we were assuming that there are no currents in our theory that have a conformal weight higher than 2. Why this assumption? Well, we know about current algebras and their corresponding commutators that have h greater than 2. These algebras are called W algebras. W algebras are hard to study because they contain nonlinear terms. These nonlinear terms impose a lot of problems if we want to make a string theory out of W algebras. I can say that constructing the BRST current is a nightmare with these algebras. The simplest W algebra is called the W3 algebra, and the corresponding strings are called W3 strings. An interested viewer can see Chris Pope's review for details on W3 strings. Talking about the second assumption requires a bit of background. When we have a current, let's call it J of Z, then the first term in the OPE J of Z times J of W has to be proportional to Z minus W raised to the power negative 2 times H. This has to be the case because of the correct conformal transformation properties. Now, if H is not an integer or a half integer, it is easy to see that Z minus W to the power negative 2H won't be single valued when W circles around Z. This multivaluedness can cause many problems. To avoid these problems, we assume that all the currents in our theory have integer or half integer conformal weights. But what will happen if we drop this assumption? We get something called fractional strings. An interested viewer can read Ty's reviews for details. It should be mentioned that there are some string theories that can't be put in this classification that we have followed. One example is Green-Schwarz string. I should also mention that there are 2 string theories called type 0a and type 0b, but these theories have tachyons in them and therefore these are unphysical. More interestingly, there is a heterotic string theory which is not very well known. This heterotic string theory is obtained by a process known as twisting. This heterotic theory neither has supersymmetry nor a tachyon, which makes it a very interesting theory. An interesting viewer can read chapter 11 of Polchinski's book for details. This theory is used for some applications. For example, it is used to study Arias vacua in string theory. Apart from studying W and fractional strings, there are some other questions regarding string theories on non-geometric backgrounds that still aren't understood very well. People occasionally come up with suggestions for new string theories while studying strings in different settings. For example, you can see this paper by Savdeep Sethi, who is also the advisor of my advisor. So, if someone asks me the question, have all string theories been found? I would say that most probably no. But a significant number of them have been found. However, you never know what the future has for us. Thanks for watching, and if you like this video, give it a thumbs up, and if you like the content on my channel, consider subscribing. Have a good day.